So in this video we're going to talk about how to calculate arc length for graphs. A graph is a curve described by y equals f of x. Alright. In such a situation, the graph passes the vertical line test, and so a picture like this makes sense. If you look at the little length ds, right, you can think about it being related to this little dx and this little dy. According to this rule, right? ds squared is dx squared plus dy squared. If I factor out the dx squared and divide by dx squared here, right, to be fair, then this suggests that ds is the square root of 1 plus dy dx squared times dx. So to find the area, or excuse me, to find the total arc length from x equals to a to x equal to b, we simply add up the little arc lengths, the little ds's, which motivates this being the arc length of the curve. So we integrate from a to b, the square root of 1 plus the derivative squared dx. Now, this method of argument I'm showing you here is called again, the infinitesimal method. That's not a proof, right? It's not a proof, and it can be established through more carefully constructed limiting procedures, but the heuristic above illustrates, anyway, the infinitesimal method. When we get to parametric curves, I'll probably give you a general proof of this formula based on an actual careful limiting procedure and a particular application of the mean value theorem. But that will come later. So let's look at an example. Here we go, example 1. My paper keeps moving on me here. A second. Forgotten where you. So example 1, we have. I'm having trouble with my paper here. Just a second, guys. We have y equals x to the 3 halves. From x equals 1 to x equals 4. We want to calculate the arc length of that curve. So dy dx is 3 halves x to the 1 half. So if we square the derivative, we get 9/4 x. Then using the star was the formula I just motivated through the infinitesimal method, we integrate from 1 to 4 the square root, but that's calculable using a u substitution, like so. Change the bounds. If I plug in x equals to 1, I get u equals to 1 plus 9/4. If I plug in x equals to 4, I get u equal to 10, like so. And so that integrates to 10 to the 3 halves minus 1 plus 9/4 to the 3 halves. The 2/3 is from the integration of the half power function. And there you have it. So the arc length of y equals x to the 3 halves power from 1 to 4 is approximately 7.634. So that's how we calculate arc length. We just have to integrate the square root of 1 plus the derivative squared over the appropriate range of x. Let's work a somewhat more famous example next. Alright. So next up, let's calculate the arc length of a circle. So here we have, of course, x squared plus y squared equals to r squared, which, by the way, is not a graph, right? It takes two graphs to put that together. Y equals to the square root of r squared minus x squared, and y equals minus the square root. Calculate dy dx anyway, we get this. And by symmetry, we can simply double the length of the top half, right? That'll give me the arc length of the whole circle. And also dy dx, when we square it, this simplifies a bit, right? We get x squared over r squared minus x squared. So this is the integral we face. Twice the integral from minus r to r, because that's r and that's minus r for x, right? So we have to integrate this according to the rule. Make a common denominator. So I do that, right? A little bit of algebra right there. The x squareds cancel, and r we're assuming is positive, so we pull it outside the square root. I'm going to scroll up here a bit. And So that x squared canceled. Square root of r squared was r because we're assuming r is positive. We're left with the square root of r squared minus x squared downstairs. Then I changed the 2 to a 4 because this is an even integrand, so I can just double the integral, supposing it exists. Let's see here. In fact, this is improper integral, right? Look at that. So, what's next? Take the limit as b goes to r from the left, and there's my integral. And then so this has an integral of inverse sine of b over r, and so we get that plugging in the upper bound, plugging in the lower bound, we get that inverse sine of 0, 0. Now the inverse sine, as we approach 1, basically the input to inverse sine is becoming closer and closer and closer to 1 from the left, and that limits to pi over 2. So we got 4r times pi over 2, which is 2 pi r. What do you know? The arc length of a circle is 2 pi r. Now this example, later in the course, once we learn parametric methods, becomes much easier. But for now, this is what we have to do. By the way, this is how I knew the integral was inverse sine. Here's the actual integral. So that is that, is that, is that, is that. It's a trig substitution. And there you have it. So, like I said, as I just mentioned, parametric viewpoint, this calculation becomes much easier, which we'll learn later. All right, so moving on here. Moving on, example 3, we want to look at the arc length of sine for 0 to pi. So the derivative of sine is cosine, so 1 plus cosine squared, integral from 0 to pi, and it's about 3.8202. I used a numerical method to calculate this integral. Not every, you take the square root of 1 plus something squared, it may or may not be the case you can actually do the integral. In this case, it's not so nice. So that's the answer, and that's sometimes the best we can do. Now, so that's something you need to figure out for yourself as you're taking this course, is how are you going to do numerical integrals, right? I will sometimes use wolframalpha.com. If I need to do a numerical integral, it's usually pretty good. Although Wolfram Alpha, www.wolframalpha.com, it knows too much. Sometimes it will give you very fancy mathematics that you may or may not want to see at that time. But anyway, there's various web applications which will calculate numerical integrals. I think even my simple $15 Casio calculator that I got from Walmart will actually do numerical integrals if I take the time to set it up. All right, moving on. Let's see here. So now that we cannot integrate everything, but typically speaking, I would probably give you a warning on a test or something if you weren't supposed to actually do the integral. I would say something along the lines of, well, I wouldn't actually ask you to calculate it. I probably would say set up, but don't integrate the arc length integral, something like that. Here's the next one. Y equals the log of the cosine of x between 0 and pi over 3. All right. So cosine of 0 is 1. Cosine of pi over 3 is, I think it's a half. So we're going from values of 1 to a half and putting to the natural log. So there's no kind of improperness here, at least for the graph. No, so let's see what happens with the derivative. Differentiate log, we get 1 over cosine times the derivative of the inside function, which gives me minus sine. So I got minus tangent for the derivative. I square it, I get tangent squared. Ooh, hey, that's nice, because we know that the arc length integral is the square root of 1 plus dy dx squared, but 1 plus tangent squared is secant squared. So we just have to integrate secant, which is not trivial, but we know how to do that. We talked about that before. So the integral of secant is just the natural log of the secant plus the tangent. Again, this can be shown using a u equals secant plus tangent substitution. In any event, there it is. And then we evaluate from 0 to pi over 3. And the 0 gives me the secant of 1 over cosine of 0, which is 1 over 1, which is 1. Tangent of 0 is 0, so the lower bound actually contributes a natural log of 1, which is 0. So lower bound amounts to nothing. The upper bound amounts to this, which works out to 1 over 1/2, which is 2, and this is square root of 3 over 2 divided by 1/2, which is otherwise known as square root of 3. So there you go. The arc length of this curve happens to be the natural log of 2 plus root 3. And again, I should probably, just as a point of warning, actually example 3 is more common to your actual experience if you just go and try to find the arc length of things in the wild, so to speak. Things where you can actually calculate the arc length like this tend to be textbook problems, which are designed, of course, to help you learn how to do algebra and analysis better. So they do serve a purpose, and since you exist in the real world and are doing these problems, I think they're real world problems. You can agree or disagree with that philosophy if you like, but as far as I'm concerned, as long as actual humans are doing calculus problems, they are real world problems. Anyway, y equals cosh, the hyperbolic cosine of x, and we're going to calculate the arc length between 0 and log 3. Natural log of 3, of course. So dy dx is sinh, and that means that the square root of 1 plus dy dx squared is the square root of 1 plus sinh squared. But hey, 1 plus sinh squared is cosh squared, which is just the square root of cosh squared is cosh of x. Because hyperbolic cosine is always positive, so we don't, generically speaking, you take the square root of something squared, you get the absolute value, all right? But the absolute value of cosh x is just cosh x again. So anyway, so we have to calculate the arc length by integrating this, which is actually that. And so the integral of cosh is sinh, so we got sinh of the log of 3 minus sinh of 0. Sinh of 0 is 0. Sinh of log 3, though, we can simplify a bit. So the definition of hyperbolic sine is 1/2 e to the x minus e to the minus x. So if I plug in x equals to log 3, I get this. Now, e to the log of 3 is just 3. This I need to clean up a little bit. To bring the minus into the logarithm, I do by properties of logarithms. That's log of 3 to the minus 1. So then e to the log of 3 to the minus 1 is just 3 to the minus 1, which is 1/3. So this simplifies to 3 minus 1/3, which then, of course, gives me, how's that go? 9/3 minus 1/3, which is 8/3. 8/3 divided by 2 is 4/3. There you go, arc length. Next example. Again, this is one of those textbook problems where we're going to, through perseverance of algebra, figure out how to do this. Let's see here. So we're faced with x cubed over 3 plus 1 over 4x. Calculate the arc length of this thing. So first of all, we differentiate. X squared minus 1 over 4x squared. Great. Then we got to square that thing, because we know where we're going. We're going to go to that formula, right? Which is 1 plus the derivative squared. So the derivative squared is this, x to the 4th minus 1/2 plus 1/4, 1 over 4x to the 4th, like so. You notice that the cross terms, when I multiply that times that, the x squareds cancel, which leaves me a minus 1/4 and a minus 1/4, which gives me that half in the middle. This times itself gives me x to the 4th. That times itself gives me what? Oh no, that's not good. Just a second, guys. That should be 16. Uh-oh. Well, let's see what happens. That is supposed to be 16. Well, let's see what I do. X to the 4th. So I add 1 to this. Maybe I made another error which cancels the current error out. Find out here in a minute. square root of 1 plus dy dx squared is x to the 4th plus, so the 1 plus minus 1/2 gives me the half. This is the x to the 4th. That's supposed to be 16, right? Let me just go ahead and put that 16 in there because I think what's going to happen and that's also supposed to be 16, 1/16, you know, 1 over 16 times x to the 4th. Oh, well, that's unfortunate. This should have been huh. All right, well, let me think through it here for a second, guys. So I think if I have x squared plus 1 over 4x squared, I think that's what I should have there probably. That squared. Alright, so this gives us x to the 4th from that times that. And then that times that gives me plus 1/4. This times this gives me plus 1/4. And that times that gives me plus 1/16, or whatever, 16x to the 4th. Right. And that is exactly x to the 4th plus 1/2 plus 1 over 16 x to the 4th. Okay. So the fix is simple. This is supposed to be a 4 here. That's a 4. This is a 4, right? Therefore, I'm an idiot. 4. Okay, integrate. Let's see here. The integral of 1 over x squared is minus 1 over x, so that 2 just wrote along, but that 2 is actually supposed to be a 4. And let's see here, so that was supposed to be an 4 times 2, which was 8. And this is supposed to be, when I plug in the lower bound, that's supposed to be minus a 4th, right? All right. Let's see here. So we get what? 8/3 minus 1/8 minus 1/3 plus 1/4. If I've not made another silly error, hopefully not. Let's see here. What's that work out to? 8 minus 1 is 7/3. And this is 2/8, so that's plus 1/8, right? So I'll make a common denominator of 24. We get 21 plus oh, wait a minute. If I make a common denominator of 24, I can't do math. Common denominator of 24, right? So I have to multiply that one times 8, which is 56. Multiply that one by 3 over 3, which gives me a plus 3. So I think the right answer would be 59 over 24. So obviously this was based on that, long, that mistake I made right up here, right? So that's the, fussy thing, right? We make a mistake at one point in the problem, it carries through, but anyway, I think it's good for me to make a mistake from time to time. Shows you that, this is how real world math goes. You make mistakes, but then you got to fix them. The key is to be watching and thinking about the reasonableness of calculations, double checking your work, right? But anyway, that's it for this video. Thanks.